All right, everyone. Next up, we have Rachel Reese with Chaos Engineering at Jet. Take it away, Rachel.
All right. Hey, guys. So this talk is Chaos Engineering at Jet. I am Rachel Reese. I know there are a whole bunch of Jet folks in the audience, so I hope everyone has been quite good to us today. To start, in case anyone doesn't know who Jet is, we are a startup. We are an F# based startup. We are taking on Amazon. We're an e-commerce company. We launched on July 22nd. Our Apple and Android apps were, named with, both in Apple and in Android, the top of 2015 from both sides. We've had way over 500,000 mobile downloads, 600,000 first-time buyers. We're doing pretty well since we've only launched on July 22nd. We are very much hiring, and it would be fabulous, fabulous if all of you guys wanted to come and work for us. Talk to either me, I have business cards, or our recruiters, or Amy and Ivan are out in the lobby. In addition to F#, we have an array of technologies here. We are certainly not focused necessarily on just one thing, but we're heavy users of Azure. As we are taking on Amazon, we are not heavy users of AWS. But we can see we use Azure websites, the queues, DNS, all sorts of things. Down here under F#, we use several different F# libraries. This is some of the ones we use. It's not a exhaustive list. React and Node and Angular on the front end. R, Python, Sass, and PDW for our data science. And then an assortment of all of our other, or not all, but some of our other technologies in green. Console, Kafka, SQL, Xamarin, Redis, Storm. So we do embrace a wide array of technologies, even though we are, I would say, F# focused, F# heavy. In case that wasn't quite enough of a recruiting pitch, I wanted to add in one quote about how wonderful it really is to work here. So I don't know if Nick is actually here today, but it really is wonderful to work here, and I will move on now. So what actually is chaos engineering? How many folks here have actually heard of chaos engineering? Figure many. Oh, less than I thought. That's fewer than I thought. That's really amazing. So it's sort of, a lot of people think of it as just wreaking havoc with your code for fun and, sort of maniacal little monkeys. And I love this image. This image makes me very happy. But little maniacal monkeys who are just going to take giant bites out of your code and do terrible things. And why on earth would that possibly ever be a good idea? How could this reasonably, be something that software engineers should embrace? Well, I saw a really amazing talk by, I believe, Colton Andrus, who works at Netflix, QCon talk a few years back or I saw it recently, he gave it a few years back. He compared it much more to a sort of controlled burn. I don't know if any of you folks have ever lived out west, or maybe they do this upstate, but there is this idea of starting a forest fire on purpose to burn out the undergrowth in a very controlled fashion, so that when an actual forest fire starts, it's not by accident. There isn't this amazing, incredible outburst of growth that's been sitting there for 20 years that completely destroys the entire ecosystem. So the idea of sort of gently burning something to make it less bad later. So it really is more the idea of controlled experiments, and specifically on a distributed system. But the idea that through these controlled experiments, you can really build confidence and understand what it is, understand your systems, understand your system's ability to tolerate failure. Because especially in distributed systems, things will fail. The network will go down. Something random will happen. There will be issues. So these are a way to sort of test out how your network will actually handle, and how your code will actually handle these issues. In addition, your code may be very, very well tested, and as developers, we like to think of our code as very well tested always because we're amazing and fabulous, and everything I write absolutely looks like that. But what about, right? What about all of the different connections between these pieces of code? How about, chaos engineering is a way to test all of these different pieces, the connections and the network and the array there. Things like, improper fallback settings, things like, outages when a downstream component gets a lot more traffic than it was expecting, and that backs up and it can't handle things as quickly as you wanted it to. So it's a way for us to have confidence in our system as a whole. So the benefits here, because we're planning these outages to happen, they do happen when engineers are awake and available, and you've sat down at your desk and you've had your morning coffee and you're ready to think and actually solve a problem. They're not happening at 3 a.m. When you've been out with your friends and all of a sudden something is down in production, now you need to fix it. It's happening when you have the time and the space and availability to gently fix something that is going wrong. It prevents later outages, much like the forest fire and the controlled burn analogy. You're having a small bit of pain now to prevent a tremendous amount of pain later. It eventually and ideally will make your systems immune to failure. If you test these things enough, you understand all of the little bits and pieces. It's just like actually testing your code properly. You test something, you figure out that it didn't work in some edge case. Excuse me. And you understand what that is, and you fix it, and you get better, and you move on, and you find new, smaller edge cases, and you find new ways of making your code stronger and better. Your engineers will also start designing for failure. If your services start going down randomly at lunch every single day, and it's a 2-hour process to get that back up because, for whatever reason, you haven't set things up correctly, you will start to think about that the next time you design a service. What can I do so that I do not have to go through this pain again, ever again? Oops. You'll also start to really enjoy this idea of testing. You start thinking, it's very much like when you first heard about unit testing all of your code. You start to be able to depend on, I have done this sufficient number of unit tests, my code is probably mostly correct. And again, I've done this sufficient number of chaos engineering tests, I've broken my code in several different ways. It's probably a lot more correct than I would believe it to be without having done all of that testing. So the principles here, very, very short, very easy to embrace list. Define what normal is for your code. Does that mean it's, it's up 24/7? Does that mean it's only up for a half an hour from noon to 12:30 every day? That could be normal if that's what normal is. And then, second, assume that will continue. That, no matter what happens, normal will continue for both a control and an experimental group. Seemingly reasonable. And then 3, the fun part, introduce chaos in whatever form that chaos can take for you. Servers that crash, hard drives malfunction, network connection severed. Find your form of chaos, introduce that, and look for the differences. See what happened. Is the control group and the experimental group, are they still performing exactly as normal? Are they still up to speed? Or did something change with the experiment group? And I did take this, I paraphrased this from a really awesome website basically called principlesofchaos.org. But going further, and this also from them, specifically build, and once you've done the very base level a couple times, build a hypothesis around what that normal is. It doesn't have to be just an overarching definition of normal. Maybe define error rates. Error rates should be less than 5%, or think about whatever metrics of interest that you want to test and to look at. And then vary events to try to get some difference there. consider your hardware failures, consider malformed responses, anything that could potentially cause some sort of failure. Run your experiments in production. And this is a fairly important one, but it helps guarantee the authenticity of what it is that you're actually doing. Yes, it is. Also, automating your experiments. Yes, it's fun to introduce chaos as much as you can and all over the place, but that gets tedious going in and randomly restarting, services, databases, VMs. If you can set this all to be random, then you can go in and start a random set of services every morning and not even need to if nothing breaks, you'll never need to check the logs and see what is actually breaking. So, a few examples. Many of you have probably heard of Chaos Monkey. When I went to Google, what is chaos testing? There was actually no way to Google chaos testing. Google was like, you mean Chaos Monkey? I was like, no, I mean chaos testing as a general science. No, but seriously, you mean Chaos Monkey? So, Netflix actually has an entire simian army now. They have a chaos monkey as they originally started. They have a chaos gorilla that will, wipe out entire VMs. I don't remember exactly, but it's huge. Just sort of bangs on everything and everything goes down and they sort of whimper back into the corner. Janitor monkey, which will go up and clean up resources behind you. Conformity monkey. There's like this giant whole list of all of their different monkeys. It's actually really kind of cool. They do some really interesting things. There's also a WAS monkey, which is actually specifically on Azure since, Netflix obviously runs all of their stuff on AWS. So how is Jet different? What is it that we're doing that's actually anything different besides using Azure and specifically using F#? We, of course, built all of our stuff in F#. So we are not actually testing in prod. That is the ideal. We would like to get there. We are planning to get there. But a couple different reasons. Most importantly, there's been a lot of socialization to convince our developers that it is worth it to break things at all, much less break things in prod, and that it's okay to do that we're testing for valid reasons. So that I am preaching that we need to, that you guys should be, testing in prod. But more interesting, we are doing SQL database restarts and some georeplication. And, we have short little scripts which basically go through, they'll start everything, set up a georeplication and stop things. Excuse me. I know that the SQL restarts actually led to us setting up the georeplication. And excuse me. Sorry. So this is one of the things that Netflix actually hasn't gotten to yet, and I think is actually really, really cool. But so once we have this set up and many other things, the way we keep track of all of this is that we're actually we're logging everything in a couple different places, and we can check our failing tests versus our list of restarts and say these 3 services we restarted around 10:52 a.m. and these 3 tests spontaneously broke around 10:53 a.m. I wonder if that's related. They don't normally break. Let's investigate what's happening here and try to figure that out. We found a couple really, fun bugs that we definitely would not have found without this, even though we are only testing in QA. In one case, we found that we had completely different settings in QA and in prod, and that we had never enabled automatic failover in one place. And yeah, oops. Small details. We also had an issue with restarting one of our new checkpointing systems, and it wasn't properly coming back up afterwards. And we would never have found that without automatically and somewhat accidentally testing this, or chaotically testing it. So I know this is a Haskell and F# conference, but I know that a fair amount of you probably don't. So how many folks actually here program with F#? It's actually more than I thought it would be. I thought it would be a really tiny minority here. All right. I'm still going to show you guys the slides in F# because I figure that many folks here haven't actually seen much F#. But I would highly recommend that everyone go out to two places. fsharp.org is the F# Software Foundation. We have a foundation. We handle the board handles sort of the much of the code, but also running the F# language and steering that. F# was open sourced 2 years before the rest of Microsoft sort of got their act together and actually thought they would be open source. So we like to think that we have it right. Well, certainly from the Microsoft standpoint. But check out so fsharp.org, and then the second one is F# for Fun and Profit. These slides I usually give to a much more introductory audience. I will breeze through them a little faster and give you a little more high-level information. But programming languages obviously evolve, much like regular languages. I don't know if you folks have ever seen this chart. I love this chart. But it basically is exactly what it shows, a history of programming languages and how they've influenced each other and how they work together. And this chart makes me very happy. A lot of the comparisons I will do to C# because a lot of folks don't actually necessarily understand functional programming coming in. But obviously C# is up here near all of these curly brace languages, and F# is here near the happy ML path down here. Magical happy ML path. A couple testimonials. Simon actually, very standard. Look, when you actually use a statically typed language and things get better, there are fewer bugs. But Simon had a very, very standard business application. Was constant 2-week sprints, constant maintenance. Everything was broken all the time. Endless new features. He and like 2 or 3 of the devs went off into a corner, rewrote the entire thing in F#, and came back and handed the new project over to the business and basically never heard anything again. He went back to them like a month later and said, "What's going on? I wrote you this new app. Is it okay?" And they basically came back and said, "Everything is fabulous and it works, and we have no more needs for this application ever again." It's now been almost 3 years, and he's still not gotten a single report. There are no bugs. There are no additional features that needed. It just actually is just out in production running. It's almost like an Erlang story. Jan did the same thing. He has since left GameSys, but they do a bunch, I know they have a poker game that they have on Facebook. Poor Jan. He worked on a Java team, and he was able to do exactly the same thing. He went off in a corner, rewrote the entire application in F# and was able to replace his entire team of Java developers by himself and maintain the whole code. Kaggle, if you folks have heard of it, a big data science, predictive modeling company. They do a lot of data science competitions, some very cool, very interesting things. But F# code, consistently shorter, easier to read, easier to refactor, contains far fewer bugs. Now, I know I'm a bit preaching to the choir on much of this, but I figure at least you guys can steal some of these stories in your own talks and your own evangelism on the functional languages. So a few actual code examples. C# bad, F# good. F# has discriminated unions good, C# bad. Again, pattern matching. F# has this magical thing called pattern matching, which you C# people have never heard of. Yeah. And I know that Haskell has slightly different pattern matching. I don't know Haskell well enough to know exactly. I know, obviously, that it has it. But I obviously C# bad, F# good. And then again, the whole thing where, if you have a discriminated union, you try to pattern match on it, you'll get an error. This saves everything in production. It's amazing. And then this one, I keep meaning to take this slide out because it's a little mean and snarky, and C# folks get mad at it. But I thought I would leave it in for this crowd. But obviously, option types, and it's good. So something that Haskell actually doesn't have, units of measure. I don't know if any of you folks remember this, but the Mars Climate Orbiter, I believe on its descent into Mars, completely blew up because two teams forgot to actually talk to each other very well, and one was using English units and one was using metric units, and that didn't work out so well. So F# basically has a feature, where you can tag any numeric type with an additional identifier that basically, gives you more information on what that numeric type is. I know that at JET, it obviously doesn't have to be scientific. It does work very well for scientific programming. But at JET, we've talked endlessly in the warehouse team about using that for some of the code. Basically saying, this is a case of item coming in versus this is an entire pallet of item coming in. Make sure we don't confuse those, because that is very important, and we don't want to ship the wrong one to a customer. There's also type providers. And in this crowd, probably nobody uses Entity Framework, but it's an awful, awful, awful ORM. And but any of them in general, 920 pages on just how to set up a connection to your database and get it to be correct is strange to me. Where here we have 31 lines of code, a few references, and here lines 13 and 14 are the actual type provider. We're declaring a type here, and in 14 we're instantiating it, getting some data context. This section here is just a query against that actual connection out to the database. And the bottom part of it, I'm creating a new row and writing that back. But in 31 lines of code, I can actually have had a few apps where I've written 40 or 50 lines of code and had that be my entire data layer, just because I was using a type provider. They're really amazing, especially being able to. You can use a type provider obviously in a REPL. Being able to instantly think about all of your code that way. Really wonderful, really fast. A good way to do, a lot of folks have done, used type providers for their data, especially with machine learning, all within a few script files. Dependency charts. This is, a TIC-spec is a standard F# project. I believe it does BDD testing, but I totally stole this from Scott Flashen, who writes F# for fun and profit. So this chart is his. But you can see, this bit of code here, follow the arrow, depends on that bit of code, follow the arrow, depends on that bit of code. You can sort of, with F#, you can sort of see how things flow and how things work. This is a C# project that does exactly the same thing. Obviously, at this point, it's almost incomprehensible. So again, F# bad, or yeah. Back up. Wait, we're not recording this. So C# bad, F# good, and then Entity Framework, which was the ORM that was on the cover of that book, if you guys have heard of it, is this one, which honestly, I can even barely see. There's some heavy lines here and one down here, but you'd need a team of 30 to be able to maintain a solution like that. So these are some of the reasons which I imagine that many of you, are very comfortable with as, mostly Haskellers, I think, and definitely functional programmers. But those are the reasons why we actually chose F#. So to actually look at what our code looks like to run the chaos, we have here we start by selecting a random instance. So, we have a hosted service, we have a compute function, which is a compute management client. It's an Azure thing. So we have this in, an async computation expression. We're doing a try and with catch exceptions. We're getting, hosted service details and sending in, the service name and this compute Azure magic. The deployment, so, figuring out where this actually is using the details, and then getting a specific instance. So basically, checking for all of the instances here, putting them in an array, and randomly picking one of them. It's not actually that complicated, but basically, we grab all of the instances of all the services that we have that are out running, and we choose one at random and return it. Return the service name, the deployment name, and the actual instance. If something goes wrong, we log it. We used to have, to make this code fit on the slide, I removed a few small pieces, mostly additional logging around, if there's only one actual role instance running, and that is the one we choose, we'll still choose it to be randomly shut off, but we'll log it that was the only one that is running, and that's bad because now we've just shut down every instance of the service that was running when we only intended to shut down one of many. But, as developers, it was your problem. You were supposed to have more than one instance up and running. So once we've chosen the actual, we want to restart one. So, we take in a compute and a hosted service, again, in an async block. And here, we select our random instance is the first thing we're doing. So we have the service name, the deployment, and the role instance. And we match, whether it's what the power state, whether it's stopped or started. So if it's already stopped, we log that and ignore it and move on. Otherwise, we continue and actually restart the actual instance. And that this restart instance just goes and actually, hits Azure and restarts the instance. It's like 2 lines of code, so I am not showing that to you guys. But the important and fun piece of code, we take the compute once we're there, we've gathered all that information, we have the actual service. We get all the hosted services. We look at an ignore list. We'll allow the developers to, if they're trying to push a new release out and they really need QA to be properly up and running and everything to work, we'll allow them to set themselves to ignore. So we keep a daily ignore list for, instances to be ignored that day, but that day only. So we get all the hosted services, we check the ignore list, and we perform a Nuth shuffle, which just, randomly shuffles them about. Do it distinct by the service name, which is exactly what you think it is. It gathers the distinct service names, so we're not, if there are 8 different instances of your service running, it's not 8 times more likely to actually get stopped. And then, we do that. We map and call the restart random instance, and we actually go and restart that. So we take all of this, we pipe it into an async parallel ignore with a 1, and that's something that we've created locally at Jet. So the parallel ignore, yes, performs the computations parallelizedly. Correct terminology. The ignore means it doesn't keep track of the actual result of the async, so we can schedule an unbounded sequence of them. Even though we can schedule an unbounded sequence of them, this 1 places a bound on how many we will actually schedule at once, which in this case is 1. And it starts each computation on the calling thread. So it tends to be faster in most cases, but we still can do a switch to thread pool and things. But it does tend to be a lot faster when we need it to, and it's kind of a clever little fun thing that we have done. And then obviously we run that right now. I went pretty fast through the actual code. Does anyone have any questions about this?
What are the tests?
What do you actually mean? Like what?
The invariant you want to test on the system.
For now, what we're doing is basically just restarting a service and or a SQL database. We haven't moved on to being able to test for something specific. So one more point of fact, Nora, who is this lovely blonde right here, is the one who is doing the vast majority of this work. I'm just an evangelist and I get to come up and speak to you guys. But I know that she is working on a lot of that. Yeah. All right. So this went a smidge faster than I actually expected, but in conclusion, Azure and F# and Chaos is fabulous and totally amazing, and I would love to see you guys all working at Jet. If you guys have any more actual questions, please let me know, and definitely hit up Nora and Ido if he is here. I don't see Ido yet, though.